Like any spectroscopy, IR spectroscopy is the observation of how a molecule interacts with light. In this case, the light used is in the infrared or IR spectrum, which is a longer wavelength than visible light. Hence the name infra meaning below, and red being the color below red. Light in this wavelength can be absorbed by the bonds in between atoms of a molecule and can cause them to move in certain ways, called modes. These modes include stretching symmetrically and asymmetrically, rocking, scissoring, wagging, and twisting. An IR spectrophotometer will provide a graph like this. This one shows percent transmittance, which is how much light passes through the sample, though this could also be an absorbance, which is how much light the sample absorbs. Various functional groups can be seen in this graph from their modes of vibrations at different wave numbers, which is 1 divided by the wavelength. For instance, this group is for ethanol. There is also the fingerprint region, which is between 500 to 1500 centimeters to the -1, which is unique for almost any compound. How this graph is derived depends on the type of IR spectroscopy used. FTIR is the major type of IR and relies on a source shining all of the wavelengths of light required at once at a beam splitter, which splits the light 50-50. Half of the light will travel to a stationary mirror and the other half at a mirror that moves, in this case back and forth. Both the beams then recombine, are sent through the sample and to the detector, which picks up the interferogram. This then goes through a Fourier transformation, hence the FT and FTIR, providing the final spectrum. Another setup is attenuated total reflectance, or ATR, where the sample is placed on a crystal. The beam of light then undergoes multiple internal reflections inside the crystal. These reflections cause an evanescent wave which extends into the sample. The interactions of this evanescent wave and the sample can then be measured. One of the applications of FTIR and ATR in medicine is the analysis of drugs, which has been proposed for things such as drug tests at music festivals, as it is a highly discriminatory method. However, it has the drawbacks of mixtures or molecules being potentially difficult to read. Furthermore, the quantification of substances, while possible, would be infeasible in the settings where drug testing is required, and thus would only act as a qualitative method. For example, these drugs are present, but in unknown quantities. IR also has the benefit of being able to differentiate diastereomers and free-base acid and salt forms. Free-base or acid forms often have a lower boiling point, allowing them to be smoked, whereas the salt form is more stable, usually soluble in water, and allows for injection. An example of this is crack cocaine, which is the free-base form, and cocaine, salt, even though they are both the same drug. Pulse oximetry is a common practice where IR is used in a hospital setting. Pulse oximetry is the equipment that measures the heart rate and blood oxygen saturation of the patient. Commonly, this is a finger probe, which shines 2 wavelengths of 660 nanometers, red light, and 940 nanometers, infrared light. The oxygenated hemoglobin in the blood will absorb more infrared light and transmit more red light. The ratio of red light to infrared light is then converted to blood oxygen saturation using a lookup table based on the Beer-Lambert law. As only 2 wavelengths are absorbed, a Fourier transformation is not required. More recently, microorganisms have been shown to be able to be detected using FTIR. The unique biochemistry of each microorganism also causes them to have unique fingerprint regions. Because of this, a bacterial sample can be isolated and grown, then suspended in solution and measured. Libraries of organisms have been developed, like those for drug detection, that the sample can then be compared with to find a match. This can also be used to produce dendrograms of similar strains. IR can be applied throughout medicine in many other areas, including functional neuroimaging, where it can sometimes replace functional magnetic resonance imaging, or an fMRI, as well as other areas in neurology. Neonatal research, as most other methods of imaging, can be harmful to babies and fetuses, and blood sugar levels, where it can be helpful for people with diabetes or similar diseases, as well as sports medicine.